Okay, so because of the way the structure is shaped, I think the math of everything is quite a bit easier if you do use this rotated coordinate system. Um, I should have made it easier in the other coordinate system, so you had to use the dot product thing. But uh, so isolating the whole structure, I got three equations for four unknowns. You can't solve anything yet. Um, because the coordinate system is here. So, you know, I mean, you can think of it as this is 20. And so that's negative 5,000 cosine 20. You know, you could do it that way, or you could do it as 5,000 times cosine of 250. Um, and then, okay, so this. Then for the moment equation, I took my moments about the point A. So there's no moment produced by this. This one, we have our force of, 5,000 cosine and sine 250. Cross product with um, the vector going from the about point to where the force is applied. And that vector is 0.5, 0.866. So if you take that cross product, this minus this, this isn't zero here. And so this is the equation I get from the moment equation. Did anyone do this like with the same about point, same coordinate system, and get the same get different answers? Did you do the same?
I did the same. I got the
So
same answer.
same things, yeah. And then I isolated member two. I called this member two and isolated that just so I didn't have to deal with just so I could keep consistent with my convention of where the force is applied and I wouldn't have to deal with that external load, you know. So I took the second member. The only forces are these. Um, by the way, if you want to find shortcuts, this is a two-force member. You could treat this as just a scalar force going that direction and um, equal and opposite force over here. Cuts down the number of variables. But so I took my moment about this point where we want to calculate that friction force. And so the only moment was produced by this. The vector from the about point to where the force is applied is negative 0.5, positive 0.866. So take the cross product with F21, and you get minus 0.866 F21x minus 0.5 F21y is equal to 0. And if you solve that set of 6 equations, you get a force at B of negative 501 newtons, positive 868 newtons. And now since I already rotated the coordinate system, I don't have to do any dot product stuff to turn this force vector into a component of a normal and a component of friction. So we can just set the friction force equal to the coefficient times the normal force. If we'd use a standard coordinate system, then you'd have to break that up into a normal force that's parallel to the ground here. Sorry, normal force that's normal, perpendicular to the ground, and a friction force that's parallel. So yeah, you could just take this vector, whatever you get here, you get a different value. And then you want to rotate the coordinate system from this to this, so positive 20.
Right, it's the same rotation, whether it's at the front end or the back.
That's right, exactly, yeah. Anyone have any questions about that one? So if this was steel, this would work. You like steel, you expect 0.7, I think, for static friction coefficient. Any questions about that one? Okay. Let's do another one. So say that you have now this structure. And over on this side, you have a roller that's supported by a square threaded screw, okay? So you can imagine it like this. We'll say that it's a right-handed thread. So say that this radius is 0.05. The lead is, sorry, I didn't put enough zeros, 0.005. The lead is 0.01. And the coefficient of static friction for this screw is 0.5. Okay, so if you have a force acting here, let's say 10,000 newtons, what's the minimum force you have to apply to this lever? Oh, I have to give that a length. Let's say 0.4 meters. What's the minimum force you can apply to that lever to lift the side of this structure? So we're looking for right where motion is impending with this screw lifting up, okay? And from the direction of the screw, you can tell that it's a right-handed thread. Yeah, and let's make those all 1 meter and equilateral.